You know that general theory of relativity is a theory which is quite different from that of Newtonian physics. Gravity that was perceived as a force emerged as a geometry of spacetime. Rather, gravity is a manifestation of the spacetime curvature, a new geometrical understanding. The question is that how do we measure this new geometry? What are the mathematical tools that could help us measure and define those angles, distances, and lengths? In this video, you're going to learn a whole new mathematical tool that would help you to understand this new geometry of Einstein, as well as learn the method, the process of learning, and most importantly, the best book, the best resources that you should go through. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to episode number 4 on this series of how to learn mathematics for general relativity. Well, as you have seen that we will be covering things related to differential geometry, but first here is a quick recap in case for those who have missed, but there is a separate playlist which I have made on how to learn the mathematics of general relativity. Thanks to you, those who are watching this video and putting up comments. Here is a quick recap and you can find the video in the playlist as well as in the I button. So in the last video we learned a lot about tensors. So we learned what is a tensor, what pivotal role it plays in general relativity, why it is important. We also moved out from the misconception that you really don't need to be mathematical genius to learn tensors. Tensors are not only theoretical, but they have got a lot of application in terms of practice. Tensors are not just fancy matrices, and absolutely they are not difficult to learn if you follow the certain procedures, rules and mathematical formulas. They are quite easy and they are basically meant to make your life easy. We also learned that what is the concept of a tensor, which comes from the Latin word tender, which is stretching, and it relates to something that is pulling and stretching. We saw that how tensors play an important role in measuring the things or the vectors in spite that the coordinates change, and that led to the famous quotation of Einstein that the laws of nature must be expressed by identical equations relative to all other systems, whether they are moving away or whatever the way the coordinates behave. We also saw that tensors play a pivotal role in understanding what is called Einstein's field equations, and we briefly explained what is called a Ricci curvature tensor, Ricci scalar matrix tensor, Riemann curvature tensor, and so on. We also learned from the last video that what was the origin of tensor coming from Dr. Voldemar Foyt, who actually studied tensors while doing a lot of researches on crystals or crystallography. We learned what are the mathematical prerequisites of a tensor. We saw that in spite of the frame of reference being static or rotated, the measurement of the vector is always done in a nice fashion. However, the coordinates actually change. So the way the tensors transform is a set of rules. And finally, we saw that how tensors actually are used to measure the curvature. So usually the Euclidean laws and the postulates, they fail when we move into curved surfaces, and how tensors make your life easy so that you can actually contract a lot of big matrices into a simple fashionable form. We also saw something very technical, which is called a covariant derivative, which is a generalization of the ordinary derivative, which actually doesn't take place, and we use something which is called Christoffel symbols, although covariant derivative is later covered in several parts of my video, which you can look into that. Finally, we came to know what are the different books of tensors: Daniel Fleisch, Prasun Kumar Naik, Words and Tensor Calculus for Physics, which actually lays out part of the tensor calculus and a little bit of differential geometry. And I have also shown you what is the sequence in which you can read those books, because sequential reading, if it is not, then it would lead to a lot of confusions. So this is where we ended the last video. It is there in the I button and the playlist. It is mostly related to tensors. You can go ahead and look into it. Now from here, what we understand as far as the third episode is concerned, that we actually move from flat space-time to curved space-time. Now, when we talk about flat space-time, we mean something like this, where the sum of the angles of a triangle would be equal to 180 degrees. And in case of Newtonian mechanics, or we can say classical physics, we assume what is called as flat space-time, where the space-time is unchanged. But when we come to this kind of a shape, I mean to say it can be a positive or negative, but it's a curved space-time. General relativity actually deals with this. And we know that gravity is a result of the curvature. So we come to know two important points. First is that the curvature is not something very inherent to space, but it depends on the presence of mass energy. That means if you put on a heavy mass or heavy ball, it would create a more curvature compared to that of the lighter ball. So depending, the curvature can vary on the mass and energy present. A massive star can cause a deeper curvature than a smaller object. Now, you might be wondering that we already know that, and we have seen tensors, how they measure. But what is the role of differential geometry? Here it comes. So differential geometry comes into play, and it plays an important role because it provides the mathematical tools to describe and analyze these curved surfaces, which are actually called manifolds. Don't worry, this is a very important concept which is called manifolds. We are going to cover manifold in this video, and this is what differential geometry comes into play. So from moving from flat place to curved space, where usual things or usual geometry is not happening, we use differential geometry. The name itself suggests something very clearly. We will look into that part of the video. But most important is that we now have to deal with this geometry of gravity. I would like to tell you what this actually means, because gravity is not a force but a kind of a manifestation of the geometry, the curvature of geometry. Coming into the next part of the video, what is geometry of gravity? Now, as you can understand, the falling apple or an electromagnetic force in Newtonian mechanics, these are all forces. That means they're either attracting each other or things are falling apart. But when we consider general relativity, it presents definitely completely a different picture, because gravity is a manifestation of space-time curvature, which leads to these, I would say, important conclusions, that it affects how objects move in space-time. And the paths, that means the straight line or whatever, we will look into that. These paths are technically called geodesics. For the time being, you can just understand this is just a generalization of a straight line. So usually the more massive the object, the deeper will be the curvature of the space-time. And remember, the curvature is not just caused by mass itself, but also energy. So if light has got energy, it too follows the curved path, because creating by massive objects, which is not explained in terms of Newtonian gravity. So this is a kind of a paradigm shift from the force part of physics into the curvature part of physics, and that is what the differential geometry actually helps you to understand. So this is again a kind of a trampoline, which you can think is a spread out sheet where there is a ball, and the ball is causing a dent. So gravity is not a force pulling objects together. Instead, it is the curvature of space-time caused by mass energy that dictates objects how to move. So this is pretty important. The geometry of space-time tells objects how to move, and the presence of mass and energy tells space-time how to curve. And this is really a beautiful interplay between matter and the fabric of space-time. This is what we understand from the trampoline example. But the question is this: how to, number one, define this geometry? I mean to say, how do we define this trampoline like stretched out or curled up geometry? Second is that how to give a mathematical framework. I mean to say, how will we define through mathematics this kind of a stretched out geometry? And third is that how to show the relationship between curvature and distribution of mass and energy. So we have already set the stage that what is the need or what is the role of differential geometry in general relativity, in order to define geometry, in order to give a mathematical framework, and in order to show the relationship between the curvature and distribution of mass energy. So here comes the answer to the question, the role of differential geometry in general relativity, in a very simple and quick manner, coming up into the next part of the video. So first let us understand this, that differential geometry is actually a branch of mathematics which provides certain tools to analyze curved space-time. The tensors, which is also, I mean to say, can be a part of differential geometry, which is a part of differential geometry. This is an exotic mathematical tool for precise calculations of how objects will move. As we saw, the tensors actually transform with a certain predefined set of rules. So when I'm moving from one coordinate to the other, how objects will move in curved space-time, this is something which they do. And also it allows to express the relationship between the curvature and the distribution of mass and energy. So this is done by tensors. Now there is a kind of I won't say a misconception, but it's a limitation with this trampoline example. Remember that this trampoline analogy gives a good starting point, but remember that space is not just a 2D surface which you can look right on the screen. It is a 4-dimensional manifold, and it is a complex mathematical object. So if it is a 4-dimensional mathematical object, then we need a strong mathematical rigor in order to define those. So that is what differential geometry deals with. So it allows to work with these higher dimensions, I mean to say 4-dimension right at this moment, and understand the relationship between gravity and geometry of space-time. So the role of differential geometry is to provide a mathematical tool in order to understand things and give precise calculations of how objects move. But it is not that it is only a 2-dimension, it's a 4-dimension. So in order to deal with those dimensions, we need something which is a mathematical rigor. Now, I hope you have seen this in the earlier video of tensors, but I would still like to tell you in this way, that special theory of relativity actually deals with what are called inertial frame of reference, speed and velocity, which is experimentally provable, obviously, if you can extend those experiments. And these actually deals with which is called are the frames of reference. From there, we can understand that obviously special theory of relativity is a theory of simultaneity. And that means it is a study of speed, time and space. On the other hand, general theory of relativity is something which deals with non-inertial frames, gravity, geometry on space-time, and which is on a much larger scale, on a macro scale, with stars and black holes and supermassive black holes and so on. So we understand that this is a study of geometry, and it deals with curvatures and surfaces. That means we can deduce from this discussion that if we move from special relativity to general relativity, it is less of relativity and more of geometry. So if it is more of geometry, definitely we need a tool that would explain this geometry. Further, as you can see, all those objects like length contraction, time dilation, transformation of Maxwell's equation, speed of light, when I moved from here to tensors, geodesics, parallel transport, Riemann curvature or Riemann curvature tensor, you can see that this is a transition not from mathematics to mathematics, rather from relativistic mathematics to geometry. And it is less of relativistic effects and more that of nature of space-time. And this, the nature of space-time, is what we call general relativity or differential geometry. So in order to define them, all of them consist geometry rather than mathematics. So we need something, a mathematical tool, rather I would say a geometrical tool, in order to define the curvature, in order to define this new geometry of Einstein. And this is what is called why we need the role of differential geometry. Remember, if you have gone through my series, which is still going on the history of general relativity, Einstein was not at all aware about differential geometry. It was his friend Marcel Grossmann from the ETH Zurich who taught him what is called the Riemann curvature tensor, etc. Otherwise, he was unable to form what is called the covariant theory of gravity. Now, this is basically what we call the role, the definite role of differential geometry. Now, from here we come to another question, is that why do we at all need differential geometry? Now, don't get confused that the role of differential geometry and the need for differential geometry are the same. No. The role is what it plays, and need is something that there is a limitation in terms of a theory, and in order to redefine that theory there is a need. So necessity is the mother of invention. What is the necessity? The necessity was unable to define the Newtonian mechanics shifting from flat space to curved space, and this is what the role of differential geometry comes into. So you can just quickly go through that. You can pause the video. Just a kind of a definition. The differential geometry is the study of smooth shapes and properties of curved surfaces directly related to the geometry of space-time. Now, I would like to give a point. I would say this is noteworthy because some people think that differential geometry originated only from Einstein's relativity. No, it started much earlier from Bernhard Riemann, even prior to Riemann. Differential geometry actually was there. So it was used later by Marcel Grossman and taught to Einstein to use that. So it has got nothing in connection with relativity. It is an independent branch of study of mathematics. What is that branch of study? You can now understand. The word differential actually means differentiation. And you can always understand that it is obviously the rules of the calculus because it uses infinitesimal differences, differentials, etc. On the other hand, geometry, if you understand, obviously is the structure where the entire physics is taking place. Now, what we do is that we use the calculus in geometry in order to understand the underlying structure where the whole physics takes place. So here is, I would say, the assimilation of these two words. So differential plus geometry, which actually focuses on the study of geometric properties using calculus. So what are the tools that they use? They use derivatives, local analysis, tangent to spaces, connection to different equations. Simple. Whatever the way you use and learn calculus, the same thing you're using, but on the geometric surfaces. Why you're using? Because it is curved, it is not straight, and there are a lot of things which are curved, and in order to measure those curvature, infinitesimal small distances, differences, angles, etc., these things are being done. So this is how the connection is being established between differential and geometry. But this is all writing, isn't it, in English? Let me show you a pictorial idea so that you can understand. So you have read this. I'm not going to repeat. The discipline owes its name due to using the ideas from differential calculus. So if you get a kind of a curved surface, whatever, don't worry, it is a positive Gaussian curvature or whatever. So you get a curved surface and you get something here. That means the physics, whatever, the motion, force, electromagnetism, momentum, whatever, the physics is actually taking place on this surface. So what you can see is this, that from the curved surface, you can understand and analyze the physics, not the other way now. That is, from physics, you're not going to the curved surface. So the entire physics, what do we mean by physics as it is taking place on the curved surface. For the physics part, we know the mathematics, but for the curved surface, we know something which is called geometry. And that is what the role of differential geometry is. Let me give you a very quick analogy. Probably you will understand better. So as you can see, these small boxes, I have actually zoomed it so that you can understand. So first is that we need to differentiate, obviously. And that is why in order to differentiate, we need calculus. And that is why, while using calculus, we see that gravity is caused due to local curvature. So the arrows are pointing towards this, and it is local in nature, remember. And that is why I always tell that differential geometry is much easier to learn because it's just the local manifestation of curvatures, etc., that you're learning. On the other hand, if you take it on a global scale, you need topology, which is a far advanced pure mathematical subject. Not only mathematical, it deals with a lot of subjects like sets, group theory, abstract algebra, etc. So we need calculus, we need to differentiate, and that is why after differentiation we can use the rules and formulas on the curved surface, and gravity is just the local curvature which happens, and we are not considering the global aspect of it. So here is a schematic diagram. So you can see that general relativity is built on the mathematical framework of differential geometry, and these weird curved lines, as you can see, these are curved surfaces, and we are using these curved surfaces. Why? Because in order to connect those red dots. For example, in case of Euclidean geometry, we need to calculate the distance, the angles, the lengths, whatever. So all these red points are where the physics is taking place, and general relativity is the physics, but where it is happening? It is happening on the curved surface. So we need what is called the differential geometry. So the curved surface manifests itself into various tensors, which is this, which is called the metric tensor, which is an integral part of Einstein field equation. The geodesic equation is also a part, because you will soon see that why geodesics are very important. And this is the final output, that the entire edifice of general relativity is built on differential geometry, and we need to learn on that. So this actually, now you see that it is actually showing you the need, the necessity and the limitations of the earlier theory and the need for differential geometry. So again, to repeat, the role of differential geometry and why do you need the differential geometry, these two topics are not the same. However, there is something more that is required. I mean to say, if you don't know differential geometry, probably you won't know these things. What are these things? First, number one is this: you need to measure the curvature. Second is that if two lines are converging, or they're diverging, or they're going parallel, you need to know geodesic equation, and for that differential geometry is essential. Here you see, if you go for a pseudo Riemannian manifold, for understanding manifold you need to understand differential geometry. Here you can see that the Ricci curvature, right, it is diverging, so also you need differential geometry. In fact, in order to understand black holes, I won't say black holes, I will say the metric of the black hole. For example, the Schwarzschild black hole, which is typical idealization situation, or even difficult situations like the Kerr-Robertson-Walker metric. Whatever you are going, you need to have a differential geometry, because all these things are taking place on a very weird curved surfaces. Now let me show you a further example, then we will go to into the next part. So if this is a globe, and possibly this is the man who is standing. Now say for example you are standing here and you're moving from here to here. These red dots are connecting the movement, just to give you an analogy. And further the person moves from here to here and so on. And it keeps on moving from here to here and so on. Right? So now we move into a curved surface. This is, I am zooming the globe into something like this. I will explain what is this, which looks like a flat surface. So the person keeps on moving from here to here, from here to here, and here to here, and finally ends up here. So here you see that this surface locally resembles a Euclidean space near each point, which is called a manifold. We will come to this manifold. We cannot skip this because it is a very important integral part of differential geometry. So what we understand from here is that if I see globally, then I can see a person moving around a globe. Now I take a giant microscope and I keep on zooming and zooming and zooming and zooming. It ultimately turns out to be flat. And this flatness is what is called a manifold. That means locally it would just look like a Euclidean space. Means that what you see the daily world around. And this is the concept of the manifold, which is very important in general relativity. And if you really want to know more, this is the global and the local. You can look into this video, lesson number 19, which is much more into details, Beginner's Guide to Manifold, where I have explained those things. Now you can understand that we need a manifold, but I was telling that we need calculus and differentiation. So where from the calculus comes in? Now you see these three structures, these are curvatures. So this one is a positive curvature. Why? Because the geodesics, we should technically now say geodesic, not straight line, because straight line doesn't happen on a curved surface. This is called a positive curvature. Here the geodesics are going parallel, so it is a zero curvature. Here the geodesics are converging. You can call it as a negative curvature. Now all these curvatures are great. We are using calculus, but why we are using calculus? Now you see, if I again zoom, or I extract a part of this curved surface and I apply the rules of calculus, that means I'm dividing and dividing and dividing into very small pieces, isn't it? That is the basic intuition of calculus. So we get a dA, for example, the differential area, and we can use the dy by dx. That means we are using the rules of calculus in order to measure this. So what you saw on the global structure, that the person is moving, the same thing we are doing on a local structure also. Ultimately it is the local structure. So we are taking out parts, we are cutting them into small pieces, and we are basically using calculus in order to measure the curvature. And this is actually what is done in general relativity, that the surfaces are not very easy to walk around, so we use calculus to do this. So now you see this yellow boxes which I have highlighted here locally looks ordinary Euclidean. That means what you see around right now around your house, around your trees and buildings, these are all locally Euclidean spaces. But one thing is very important which we have skipped. Now the important feature is that a surface is smooth if it is locally homeomorphic to a Euclidean plane. What do I mean by homeomorphic? I will come to that part later. But understand this, that if this is what we saw, that from global we move into local and each point resembles an Euclidean plane, then from here all those this white points, isn't it? We are using the calculus. What we can see, these are isomorphic. That means Rn, that means real number raised to the power n are isomorphic to x1, x2 dot up to xn. That means the surface is smooth. We will come later, not in this video, what is a smooth surface, what is a continuous, smooth, etc. Breck surfaces. But the surface is smooth and is locally homeomorphic. That means, let us understand homeomorphic, something which is, we can say, equal. But in true mathematical sense, again, it is not. Homeomorphism is not equal. Neither it is isomorphic. Homeomorphic is homeomorphic. So here is the definition. If I take a function f, which is continuous, then its inverse f raised to the power minus 1 is also continuous. That means here you see the animation, this donut which is now you turned into a coffee cup, then again this coffee cup is going in an inverse and it is turning into a donut. So again from the donut back to a coffee cup and the coffee cup back to a donut. Now this is, I understand it's a classic example of topology, but let us understand, because differential geometry in some part will be related to topology. So any surface we take, extract it, we do the calculus, and if we see that the surface is locally homeomorphic, that means the function and its inverse is continuous, then we can say, okay, this is homeomorphic, and we can say that we can use the rules of differential geometry. So smoothness of a function is what we call is a property which is measured by the number of continuous derivatives. We do derivatives and the derivative and the derivative and so on. So continuous derivative means what? That the function is differentiable and its derivative is a continuous function. There is no break. So f is differentiable, so f prime x0 is also continuous. So this is an example of a differentiable function. This is also differentiable, but this is not continuous. It is non-continuous. Why? Because the line has got a break. So again the same example, if I take those black boxes, what I see, this is a differentiable function. It is a differentiable structure rather. Why? Because it has got a continuous function. And this part which I see here, it is what is called a continuous derivative. We won't go too much into the mathematics this, because I have already made earlier videos on this. So from here what we can understand is that manifolds are actually a universe. It is a universe which is modeled for a four-dimensional space-time so that the spatial coordinates are defined. This is something again very specific to differential geometry. There are certain things which are called charts and atlases, and these are different coordinates to describe various regions of space and time. This is something which is called a tangent and a cotangent spaces. A little bit technical because it is used in integration over manifolds. And if you really wonder how does a chart looks like, this is a glimpse from an earlier video. This is what a chart looks like. From here you move into this, and then you take a composite function, and then you do a inverse, and when the chart interacts you take a transition mark. I don't want to really go into that. You can look into my differential geometry playlist, you will understand that. So what we can deduce is this one, that differential geometry we need because we need differential forms of integration such as Stokes' theorem, which relate the flux of the fields through a surface. So if a particular body is moving, how do we calculate the flux of a field to the surface? And this is what differential forms and integration require. Connections and covariant derivatives, I have shown it in many of my videos in General Theory of Relativity, that in order to look for the torsion free part and what is called the parallel transport, you need connection covariant derivatives, and Ricci-Riemann curvatures, etc. are definitely which are required. So now we understand why do you need differential geometry, really, because this is a kind of a surface where things are taking in a different role. So we use calculus, we use those in order to understand the local nature of the gravity and so on. But as I told you, that one thing which was very important is the concept of manifold, and you cannot ignore manifold in order to learn general relativity. That's very, very, very important. And that is the part which we will cover in the next part of our video, which is called manifolds and general relativity. This is super important, so please do attention and pay attention and don't skip any part of the video, because this is the foundation base structure on which the mathematics of relativity is built. Now, I was going to my college one day, and I was, really surprised when a truck was standing by my side, and I saw the word manifold, which was written just below the gearbox. So I then came back and I started to go into internet, Google, ask my father that what actually is manifold. I was thinking that manifold is something which is only related to mathematics, but I was wrong. So as you can see, these are some of the photograph, because I really want to make you understand that you don't have a misconception. All these engineering structures, you see what is a manifold, instrumentation manifolds. From Wikipedia, I have taken few lines. There's a kind of a pressure. What is manifold leak testing? So ultimately, if you go to internet and if you are really aware, and if you could see a nearby truck which is stopping, you will see this word manifold. Because manifold is a fluid or gas distribution system or device that serves to bring many valves into a single place or in a single channel into an area where many points meet. I mean to say, overall, the idea philosophically it is the same. Because if you're trying to bring in gas distribution system into one place where many channels are connecting, here also we are doing the same thing. We're trying to use calculus so that we make things easy. So this is one manifold also, so don't get confused by that. And what we are more importantly using is this manifold, that it is a space that locally resembles familiar Euclidean space but can be globally quite different. Now the importance is that if you can understand the local structure of a particular model, any mathematical or physical model, it is easy for us to use calculus and those known mathematics, and then then formulating the mathematics would be much easier. So as you can see, the entire structure of mathematics is built on this, that is the manifold. And if I zoom this manifold, so I use this magnifying glass, what I see, it is just similar to what we see in a daily life. That is, it is locally Euclidean. So manifolds definitely provides a mathematical framework for the fabric of space-time in general relativity. What is also important is that manifold definitely have different dimensions, and that is why it is very important, because Einstein's relativity, general relativity, uses 4-dimension space-time, 3 spatial, 1 temporal direction. So if you take a beach ball, which is a 2-dimensional manifold, you can move up and down and around, but space-time has got a 4-dimensional manifold. Now here I would like to make a very important point. I'm going to show you that manifolds, as you have seen earlier a few minutes back, that it is mathematically uses a concept called homeomorphism. And homeomorphism something means that I will show you now a illustration, is like a smooth stretching of that sheet that allows you to map a small flat patch of the beach ball to a flat region in Euclidean space. Now here comes an example. So a donut and coffee cup are homeomorphic. We have just seen the animation. I hope there is no confusion. That means if a donut can homeomorph, again it is a wrong English, I should say if a donut is homeomorphic to a cup, and the cup again through morphing gets back to a donut, then obviously this is true, isn't it? We'll share some common features. Now think deeply that if donut and coffee cup are homeomorphic to each other, that means the function and the inverse of the function are continuous and smooth. That means if they share certain common features, then if we can define a physics which has got the same homeomorphic characteristic, then understanding the physics in all those surfaces which are homeomorphic to A, B, C and D, isn't it, it will become easier. Won't it serve our purpose that understanding one surface can really smooth our life to understand others? Let me show you a quick illustration. So here is a cube. Okay, just try to think that you are blowing air into that cube and it blows up like this, and then it goes up like a beach ball or a volleyball or whatever. So it is homeomorphic, it is continuous, it is smooth. The inverse is also true. So if I get some amount of physics, whatever the physics is happening around this part of the, this part of the cube, The same will be applicable of the physics around this, and the same will be applicable and the physics around here. So all those circles mean the physics which is happening locally. So locally the physics happening from this to this to this are all the same, and that is why it is very important tool to understand homeomorphism, because all of them will have common features. All of them will have common features. So that is why we need to understand manifolds and the concept of homeomorphism. So now you see, if I take three surfaces, the flat, the positive and the negative, then we can say that manifolds actually allows us to describe the curvature of space-time in a very rigorous mathematical way. Why rigorous? Now you come to this part again, that if I get the surface of this and this and this, and I know that they share a common feature, then learning the physics will become much more important. I would say much more easier. So, and also it happens that the muti of the manifold is independent of any specific coordinate system. You see, the negative curvature almost looks like a potato chips, which has got a negative curvature. It looks like a ball. This looks like a flat piece of paper. So all these are happening, but it is independent of coordinate system. So that is why, because general relativity is independent, as Einstein's quotation again, that whatever the way things are stretched or strained or done in several ways, manifolds or the manifolds will be the tool in order to measure the curvature. That would stay invariant. The question is again going on your mind is that why you should learn manifold, and the answer is obvious. You should learn manifold because, as you see, the sets of points are locally familiar to Euclidean spaces, like a flat plane, but can be globally quite different. We have seen, just like a sphere. So if it is from a flat, it is moving into a sphere. So what is happening is that there is a curvature change, and this curvature change, how you can measure that? It is mathematically rigorous. It should be mathematically rigorous. That is what the manifold does. And space-time in general relativity is modeled on a four-dimensional manifold, and each manifold actually represents a specific event. And you know that Minkowski space-time, what it calls? It calls as an event. And that is different by null geodesic, time-like geodesics. I am not going onto those. And most important is this one, the beauty of manifolds, because mathematics is a very beautiful subject, is that they are independent of any specific coordinate system. You have seen numerous occasions, numerous examples, how I have shown these examples, that there is a stretch, there is a pulling, there is a scaling, there is a reduction. The laws of physics in general relativity should hold true, irrespective of the chosen coordinate, and manifolds actually helps you to do that. So that is the reason you should learn manifold first, at least have a kind of a basic, if not a rigorous mathematical understanding. Okay, now we understand that we need manifold, positive curvature, locally Euclidean, homeomorphism, but where are the resources? What are the books? There are so many books on manifold, isn't it? But which book to select and how to learn that? Coming up in the next part of the video. I won't show you much, huge amount of books, but just few books which are going to be a Bible. Those are very easy books. Now the first book I would talk about is Loring W.T.U.'s An Introduction to Manifold. As per the Amazon rating, it is 88%. I won't be surprised if it is more than 100% even. It's a wonderful book. Around, say, this is Springer publication, 410 pages. As I always tell, fatter book is better than thinner books. Now, he is a very famous American mathematician, Loring W.T.U. He attended the McGill University of Princeton, completed his PhD at Harvard University, and who was his doctoral advisor? The famous Philip A. Griffith. And I hope you all know the famous book of Philip A. Griffith. If you know, please let me know in the comment section of this video in the channel Physics for Students. Now, here are quick highlights I would like to tell you. You see that all these are basically from Shashwati Mukherjee, and these are, I would say, reviews from Amazon, which tells actually one simple thing, that it is absolutely a wonderful book. It is an easy book and it covers a lot of details. What are the details? We are now looking into the next part of our video. So you can see I have just taken snapshot of the content. So smooth functions on Euclidean spaces, tangent vectors, then it covers exterior algebra, dual space. The chapter 1 is basically the Euclidean space. And that is what mesmerizes me, because the books make makes you ready that before going into chapter 2, which is manifolds, smooth maps, as you can see from page 48 it starts. But before going to that page, it gives you a very good understanding of Euclidean space. And that is the brilliance of this book, as well as Professor Loring W. too. So submanifold categories and functions, all those things are required. You can just take a pause and look into the overall structure and the content of the of this video so that you can understand. Even Lie group, Lie algebras, obviously the exterior derivative and the integration, these things are being covered. Further, it covers what is most important, which is called the DRAM theory. Then it covers homotopy invariance, as I was telling, homotopy, homology, these are important, and it goes into appendix and so on. So the first chapter of the book is Euclidean spaces. I've just taken snapshots so that you can understand how beautifully and very simply it started with tangent vectors. Then it goes into vector fields. Then you take those vector fields in the figures, etc. Then the exterior algebra of multi-covectors. Remember, these are not manifolds. These are just, I would say, preparation techniques which are being done. Then it goes into Riemann's, a little bit of history of manifolds, topological manifolds, smooth manifolds on a manifold. Then it completes what is a very important and interesting for me favorite part, which is called diffeomorphism. So homeomorphism, diffeomorphism, these are all related to manifolds, the inverse function theorem and so on. Okay, have a look on this. This is a wonderful structure. You see now this one, this psi f with a complex function raised to over. So it actually shows the invertible, that chart atlas, the map F, that is how it shows. So the manifold part, it actually covers, you can see topological manifolds, smooth manifolds and so on. Then it comes into what is called a quotient topology. Yeah. But one thing you have to be aware that this book also covers topology, which might not interest you, but that is how the book is being meant. Then it covers a lot into tangent space, as you can see, submanifolds, the tangent bundle, vector fields, categories and functions. Then it covers a lot, it's a lot into Lie groups and Lie algebras. So the Lie bracket, Lie algebra and Lie group is being covered. Then the most advanced topic, which is called the differential form, which includes differential K forms, exterior derivative and so on. It also covers integration, manifolds with boundary and so on. The DRAM's theory is also being covered, and a part of cohomology is also taken into account. So this book of Loring W2, I can summarize that it is very well arranged and a very well designed book. It clears all the concepts of learning manifold. It is one of the easiest book to start learning manifold. Language is simple, the equations are also very understandable, and they are not very complex. To say this is an overall, I would say, my honest review on Loring W2's manifold. But an introduction to manifold is not all that you need to read. You need to go through another book, which is this one, an introduction to smooth manifold. Now, why you might ask why it is not smooth, why it is not differential manifold. I will come to that later, because differential manifold is a little bit complex to learn at the first go. The famous John M. Lie, Lie's book is kind of a Bible. This is the Amazon rating. The book is even fatter than the earlier ones. It was 400 pages. This is around 708 pages. This is the beautiful Dr. John Lie, American mathematician, specializing in differential geometry. So you got the master who would be speaking on this, and he graduated from Princeton University in 1972. So this is a quick review on the Amazon feedback, the best differential manifold, the great introduction to the subject and so on. And you can see now I will cover up the content. So again, it starts with smooth manifolds, goes into smooth maps, tangent vectors, cotangent bundles and so on. I'm not going too much into that, because you can at any point of time just pause the video and look into that. What is important is that it covers a lot of tensors also. As you can see, the tensor and tensor fields on manifold, symmetric tensors, exterior derivatives, these are also being covered. Orientations, integration of manifolds, DRAM, cohomology, Lie groups and Lie algebras are being covered. So what I can say, what is an important feature of this book is, look into this. This is which I have underlined. Now, you see, John Lie says that this is a first year graduate text on manifold theory. Okay. And it says for students who already have a solid acquaintance with general topology. This is really worrying, but I am going to clear up that worry, because I'm going to show you books which are not assuming topology. So it clearly says that it is assumed that you know a solid acquaintance with general topology. The fundamental group covering spaces as well as basic understanding of linear algebra. So you need to know general topology, the fundamental group, the covering spaces, linear algebra and linear real analysis. Why? Because you need to go through certain proofs. The book is similar in philosophy and scope to the first volume of Spivak's classic, though perhaps a little bit more dense. Here you see he writes, Professor Lee writes, I try to keep the approach as concrete as possible with pictures and intuitive discussions of how one should think geometrically about abstract concept, but without shying away from the powerful tools that modern mathematics has to offer. This is tremendous. So he tells right at the beginning that the approach of this book is to show that how you can think geometrically about those abstract concepts, which are very much equations, but you should not shy from using those powerful tools which the modern mathematics offer. This is also something important. But remember, you should have a solid acquaintance of general topology, real analysis and so on. And if you don't have an understanding of general topology, where will you go next? That part also I will be covering. So just quick highlights on the books on manifold. As you can see, this even what I once made a video, very small, very less in terms of content, what is called immersion, embedding and submersion. Actually it is of great interest that you put one figure into another, but this is also being covered. Submersions, immersions and embeddings, what are they called? It also covers a lot into algebra of tensors. Then it covers the advanced topics quite in details, which is called differential forms. Even symplectic forms are covered. Now if I take a comparison of these two books, Loring W. Tew and John M. Lee, I would say go for Loring W. Tew's book first, Introduction to Manifold, not to go immediately for Introduction to Manifold, because not only it is more mathematical in nature, but it assumes that you know a lot of topology. I mean, it's a general topology. So this is what we call is the book on manifold. Now if I come to the next part, that maybe you are not a book reader, because nowadays I see a lot of people learn things through online. So what are the best online lectures on manifold? Remember that I'm spending a lot of time in giving you an idea about manifold. The reason is that manifold is terribly important. So first is the University of Notre Dame, and this is one lecture. You can look again, you can pause the video, take the URL and type it out. This is from Liviu Nicolaischi. Maybe my pronunciation again is not that correct in French. So this is from the University of Notre Dame. It is quite recent, November 9, 2022. It's a good lecture which you can go through, and it covers a lot of manifolds, Riemannian geometry and so on. This is quite intensive. You see that it is almost how many? 649 websites, I mean to say pages on the internet. So you can definitely go through this. The next would be very famous MIT, Massachusetts Institute of Technology, MIT OpenCourseWare. It has got a very open-ended lectures. It starts with manifolds definition, and remember all these are in PDF format, so very well you can download all those books. I'm trying to give all those links in the description, otherwise the description would be too long. Now this is from the what is called the Radboud University. You can look into the manifold lectures, a little bit older, fall 2017 by Ion Markut. You can have a look onto that. This is a very good online lectures on manifold. I would say these are YouTube videos. This is on topology of manifolds, and it has got, as you can see, 21 videos. This is quite good. The Bright Side of Mathematics, this is also a YouTube channel which covers up a lot of manifold videos. This is my favorite, and you can see there are total 25 videos. 25 videos on what you call lectures on manifold. Then you can look into Robert Davy, is a tremendous person, got great lectures on manifold. So you can go into Tensor Calculus, Robert Davy, and you can see there are a total of 12 videos. You can look into this is this is a wonderful illustration right on the channel art. You can see the Klein bottle, etc., and with the partial derivative, how beautiful it is done. This is called Manifolds in Maryland. It's a typical name. It is my favorite, and it covers around 5 videos, but all of them are quite good. So these are all online lectures. Another is Bengaluru NPTEL, that in Indian Institute of Science, Bangalore, and this has got 69 lectures, huge amount of lectures starting from part 1, part 2 and so on. So these are all YouTube channels, all are lectures on manifold. This is another one, undergraduate mathematics. It has got how much, around 30 videos, but these are on differentiable manifolds, but you can definitely go if you are interested in. And this is also Daniel Chan Maths. This is a very good channel, which is my favorite, and it has got around 6 good grade videos on manifold. So it is not that you have to go through all of them, but these are quite a good number of channels, good number of links, which will make you understand about that. Now, having told about the lectures, the books, as well as online videos on manifold, we now turn our attention to the main part of general relativity and differential geometry. And among them, I'm going to brush over one very important topic, which is called metric tensor and general relativity. The first misconception that I want to clear to all the viewers and subscribers and professors who are watching, most of the people think that, say for example, this is a cube. I mean to say, I just assume this to be a metric tensor. So the metric tensor is not something again related exclusively to relativity. Metric means measurement. Tensors you already know. It is not specific to general relativity, but it plays a crucial role in different areas of differential geometry, including ... I have not measured those. So this is something that it is a fundamental concept of differential geometry. So metric tensor, what is that? What it does is that it covers a lot of Riemannian geometry. It is not the right video to talk about Riemannian geometry. It also covers the angles, distances, so on, pseudo-Riemannian geometry, and obviously it is the pivotal force of general relativity. So actually what the metric tensor does, that it measures distances, causal distances, for example. So here is an xy Cartesian coordinate, and I get a curved line, and if I draw this on a spherical or on a globe, it would look like this. As simple as that, nothing more than that. So understand that you need to learn metric tensor in differential geometry to learn general relativity, because it includes data about lengths, areas, volumes, again differential volumes obviously, with specific coordinate systems or manifold. So it actually I would say encodes, or it actually dictates how you would measure distances. Now distances are not similar to that of Newtonian mechanics. It has got a lot of ifs and buts and yes and no, but that is what metric tensor does. It has nothing to do specifically with relativity. It is an inherent component which is taught widely in universities in the paper of differential geometry. And if you want to know more about metric tensor, go to this video, which has gained a quite lot of popularity. 2 years ago I have made. It is a long video, but it covers every single details of metric tensor, including the derivation of the line element. The next thing which comes about metric tensor, you saw that we draw a line. That line cannot be called as a line. That is, in terms of Newtonian mechanics or Euclidean space, we call line. What we call is a geodesic. I'm not going to derive geodesic equation or nothing on that, but I'm going to tell what is the geodesics and what role it plays in general relativity. So you can see the definition actually tells that it is a curved space-time, and it is analogous or similar to straight lines in flat space. That's it. So differential geometry is something which is just similar to a flat space, and it actually geodesics are curves that generalize the concept of straight lines. So if you get a curvature like this, again following the trampoline analogy, we get this curvature is not just a dip, it is affects how objects move in space-time, and these movement of the objects are basically called geodesics. That's it. We need to learn this much only for the time being about geodesics in general relativity. We turn our attention to the core part and to the final part of our video, which is called what are the books of differential geometry. And I won't mention again many books, but certain books with their honest reviews so that you can understand. But before going to the book, I would like to address that issue which I told you about Loring W2 and John Lee's book, that differential geometry books are divided into two parts. First, it assumes that you know topology. Second, it assumes that you do not know topology. We will go forward with this one. If you're going for assumes that you know topology, you should go for self-complete books, but that is impossible. That would teach you topology and then go into differential geometry. But go for the second approach, books that assume you do not know topology. And among them, the first book, this is the green tick, right? So we are going ahead with this. And among them, the first book would be this one, which is a very simple book, which is called Curves and Surfaces. Before moving into the differential geometry part, Marco Abbott and Francesca Tovena's this book is an absolutely gem. Because why? Because it basically speaks about point number one, which is called the curved surfaces. Now here you see why I have highlighted. We do not require you to have been exposed to algebraic topology, whereas the other book was telling you should have a solid understanding of topology. So I told you that I will go with the next approach. So if you do not have any idea what we are talking about, do not worry. And for this, section 2.2 contains a complete introduction to the theory of degree and so and so. So it assumes that you do not know topology, and that is a good news. The second thing is that you look into the content. So it starts with local theory of curves. So it is just the curves, which is the first part, and then it takes you ahead. And from this it goes into local theory of surfaces, curvatures, transversality, tubular neighborhoods, and so on. It also covers areas like curvatures. Most importantly, here you see the geodesics, the Gauss-Bonnet theorem, and the global theory of surfaces. Now, the next book which comes across is called Curved Spaces. This is also preliminary step number one, and this is by P.M.M. Wilson. This has got a fair amount of good reviews. 85% is tremendous, and this is Professor Pelham Wilson. So this is also by Cambridge, and this is quite a good book to study. Now this is also quite good because it starts with Euclidean geometry and it goes into spherical geometry, then into triangulation and Euler numbers, hyperbolic geometry. So these are, these are definitely differential geometry, but step by step we are going at. Then it goes geodesics, Gauss-Bonnet theorem, and so on. So it is an excellent introduction to the field of differential geometry, and it is self-contained exposition of undergraduate geometries. That is what is important. It should be very self-complete, and it should not assume anything. This is a very good book by Bankoff and Lovett, Thomas Bankoff and Stephen Lovett. Although its rating, don't go by the rating because the ratings are almost not perfect. Stephen Lovett and Thomas Bankoff, this book is equally good. And why? Again, I have underlined. We shall not prove these assertions, as a proper discussion of simple connectedness would take us too far into the realm of topology. That means the proofs, whatever you will get, again does not assume topology, and that is the good news. Again, the reader should feel free to either skip the technical details of the proofs in the rest of this section referred to so and so. That means you can skip that, and that won't actually harm your learning. So these things are also important. Similar to in this that is outside the scope of this book. So why I am showing this? Because this is a good way in which you can actually judge a book about your knowledge and their assumptions. They assume something, you don't know something, so the purchasing of the book is a wastage of time and money. So check on these points which I have highlighted. You can skip, and it does not contain algebraic topology. It is outside the scope, and then you can go into the real part of the book. So here you see Andrew Priestley's book, which is called Elementary Differential Geometry. It is perhaps, I would say, I haven't found any book as easy as this, one of the clearest and most accessible texts. Why accessible? Again, for readers familiar with point space topology, so and so and so. So it again gives you a very clear idea. It is a very self-complete book. Again, those lines are important. Providing global results about curves often requires concepts from topology. Since we are not assuming, this is important, since we are not assuming that readers of this book have extensive familiarity with topological ideas, we will not be able to give complete proofs of some of the global results about curves that we discuss in this chapter. So that actually makes things very clear. So elementary differential geometry has got this type of I would say ideas. The books on differential geometry, the examples on surfaces, first fundamental form, and so on. It's further covers of areas in geodesics, hyperbolic geometry, minimal surface. I can tell you this is quite easy. Anybody, you can just pick it up, relax on your sofa or couch, and you can go through this book. The second one is called Christian Barr's Elementary Differential Geometry. Again, it has got a fair amount of customer reviews, not much. And this is Professor Christian Barr. Good part of the book is that he is a German mathematician. His research is mainly differential geometry and mathematical physics. So just to give you a quick snapshot of this area, Euclidean geometry, curve theory, inner geometry of surfaces, and so on. Anybody who's interested can pause the video and you can look into that. A fair around 300 plus pages of books containing a very precise, clear understanding of differential geometry. It has got beautiful colored graphics also. Then comes the famous Barrett O'Neill's Elementary Differential Geometry. This is Professor Barrett O'Neill. A little bit, I would say, mathematical in nature, because he himself is known for his contributions to differential geometry, author of 18 research articles and so on. So here is a quick review on the chapters. Again, you see the introductory part mentions knowledge of elementary calculus and linear algebra. So the book presupposes, that means what is the assumption? Just knowledge of elementary calculus and linear algebra. And the reader will, for example, frequently be called upon to use the chain rule for differentiation, but the proof need not concern us. That means you just need to know how chain rule works, but you are not worried about the proof of the proof is not concerned, and that is quite good. If an author makes this kind of a clear statement at the beginning of the book in the introduction, that makes a lot of difference to the readers. So you start with calculus in Euclidean space. You see how beautifully curves on Rn, then it goes into frame fields, Euclidean geometry, calculus on surfaces, simply using calculus, nothing else. So book is clearly a classic start for your differential geometry. Perfect introduction, very concise but not too terse, well organized, good subject and content, not difficult to grasp, and it's an excellent introduction. Remember, it's just taking an introduction because it is assuming only calculus part, and it has got many exercises which makes it appropriate for study. I won't speak of this because you all understand this is the famous Michael Spivak's 4-volume of Introduction to Differential Geometry. Prerequisites: multivariable calculus, strong background of linear algebra, abstract algebra, and point set topology. So it is very dense, very mathematical. I just thought that I should give you an idea of this. Now here is a beautiful book. I mean to say, even I use in a lot of my videos, Tristram Needham's Visual Differential Geometry and Forms. Remember, Dr. Professor Needham is a British mathematician, and his academic advisor was none other than the Nobel laureate Dr. Roger Penrose. Now the good part of this book is that it is not only covering differential geometry using a lot of visuals, but it is also covering a lot about physics. So this is some of the quick glimpses from the Amazon review. Excellent, looks like another classic, and so on. Obviously it is a classic. Now if you start with the book, I have just given a very detailed content. Why? Because it is important. It starts with Euclidean and non-Euclidean geometry. It starts with nature of space, Gaussian curvature, etc. I have read this book. It contains great interesting stories from the history of mathematics. Then it goes into metric, Beltram's insight, complex visual, complex analysis, and so on. Here you see it goes into parallel transport, which is very important for general relativity, the parallel transport and the covariant derivative. Then it covers up areas like this, the theorema egregium, that is the famous Gauss's theorem. Then it covers into metric curvature formula, neighboring geodesics, Jacobi equation, and Gauss-Bonnet theorem. So it's quite a dense book and it covers beautifully. Now here you see This now covers a lot of general relativity also. Here in this box, which I have just highlighted in red, as you can see this, it covers covariant derivative, it covers Riemann curvature tensor, symmetric of the Riemann curvature tensor, and so on, and historic notes of the origin of Riemann tensor. Beautiful. So you are directly learning general relativity in correlation with differential geometry. So a bundle of geodesics, etc. Riemann's curvature is covered. A lot of general relativity. Here you can see introduction, the happiest thought of my light. That is what is called that, what I would say, the equivalence principle of Einstein, isn't it? The space-time metric, Einstein's vacuum field equation, Schwarzschild equation, Einstein field equation with metrics, gravitational collapse of black hole, and so on. So very important read, very important book, not only for learning differential geometry, but to understand the relation between differential geometry and general relativity. I would highly recommend this book, 5 out of 5. And you see the lastly here it tells the greatest blunder of my life, that is the cosmological constant. So what else is left? You cover general relativity, you cover differential geometry, you cover history, physics, everything in one single book. The last book would be T.J. Wilmore's An Introduction to Differential Geometry. Yes, it's a good book, very clear in terms of understanding the topics, as you can see here. And it also covers, I'm so sorry, this should be here. So lines of curvature, differential geometry of surfaces, and it also covers these topics. And out of that you can see covariant differentiation, Riemannian geometry, the metric, the geodesic curvature, curvature tensors, everything is covered in quite in details. Now this actually concludes our today's lengthy discussion on episode number 4, How to Learn General Relativity, covering all the books, essential topics, online, offline, learning pattern, the books that you should not go for, books you should go for, the concepts of differential geometry, and so on. So thank you very much for watching this video. Please do subscribe to my channel Physics for Students by clicking on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can contact me at this email ID, and you can subscribe to my other channel General Relativity Explained, which is exclusive to putting up videos only on Einstein's General Theory of Relativity. You can further follow me on my Facebook, LinkedIn, Instagram, and Twitter account. Don't worry, the series have not yet been finished. There are a few more episodes which are finally lead to the conclusion of the mathematics of general relativity. Do let me know how you are liking and enjoying this series, and I will be coming up with few more videos and more videos, and Physics for Students will keep you surprising with more knowledgeable videos on physics and mathematics. Till then, goodbye. We'll meet you soon. Goodbye.